So good afternoon, everybody, and welcome to this new online technology meeting. My name is Antonio Castelo. I'm technology manager at Epic. I'm very happy to be today here to talk about optical metrology solutions for the industry. We have a very nice set of speakers to talk about different technologies and also different applications. We are going to cover metrology for different kind of materials, different kind of products, and I think it's going to be a quite interesting meeting today. Just a few words at the beginning about Epic, in case there is somebody in the room that doesn't know Epic. We are the European Photonics Industry Consortium, and as you can see in the screen, we are an association of more than 800 companies and research centers that are somehow related with the photonics business, and our goal is to connect people to ensure the sustainability of the photonics business in Europe. We offer different benefits to our members, so we help with their technological requests. We also help us in this meeting to have good networking activities and connections with companies from the whole supply chain. We help also with market reports and access to different markets, and also collaborate with a website Jogging Photonics for human resource support. And of course, we put in contact investors with companies, spin-offs, and startups that could need the money for growing and for the next activities. Just a short summary about future events. As you know, we started with a lot of physical events in 2023. There are still some of them in this last part of the year. We have one in Optic in Munich about the quantum photonics technology, another one about the laser applications for the battery manufacturing processes in Stuttgart. Also microelectronics and photonics, and two sides of the one coin in Munich, and the photonics assisted cancer pathology and surgery in Antwerp, in Belgium. And combine it also with members delegation trip that we still continue doing in different countries, and also an investors meeting in Eindhoven, in Netherlands, for all the Epic members that want to be connected with investors. And also some online meetings that we will continue doing. Some meetings in related with technology, as you can see, LiDAR on chips, optical design, simulators, and new meeting for developments. And we continue doing also marketing meetings, also technology reports, like this one in freeform optical system that I guess it could be interesting for some of you, and also in sustainable photonics. So I encourage you to go to our website and check our next event and register for the ones that are interesting for you, or come back to me if you want to discuss the details of any of them. We are also involved in different European projects, as you can see in this slide, and in particular for this meeting, we have the collaboration of two of them. MEFAB, that is a pilot line that is dedicated to help companies in the to advance the developments of medical devices based on photonics technologies, and also Pulsate, that is a network that help companies to try or to implement laser-based advanced and additive manufacturing in the processes. So if any of these cases are interesting for you, please also let us know so we can put you in contact with both networks. And let's go with the meeting today. As I mentioned, optical metrology is a very interesting topic. It covers, I think, most of the industries nowadays, from semicon, optics, microoptics, automotive, metrology is everywhere, with inline measurements, offline, laboratory, R&D. And first, we want to thank our sponsors, because all these meetings that we organize, they need also the support of Epic members. So today we want to thank the sponsors, Actar Advanced Coatings, also Essent Optics, and also Modulite. So now I'm going to introduce you first Taras from Essent Optics, that he wants to say a few words about his company. So Taras, whenever you're ready. You're muted, Taras.
Yes, thank you very much, Antonio. It's a pleasure to be here. Hello to everyone. It's both a pleasure and privilege to support the Epic events like this one. I will grab a few moments of your time to briefly explain what we do and how we do this. We are 14 years on the market, designing and building spectral photometers specifically to measure coatings, inspecting coatings for transmission and reflection. We do this both on flats and lenses, and to shorten my presentation, I will focus today only on flats. So on this slide, on the left hand, you see the instrument which is called PhotonRT spectrophotometer. This is a most hot selling system on our portfolio. We were able to place 6 different configurations in one body relative to the wavelength range. So the shortest range is from 380 to 1700 nanometers, and the widest range is the most knowledge intensive, covering the wavelength range from 185 to 5.2 micron. And we do this for transmission, for reflection, for flights, cubes, prisms, from 0 to 75 degrees angle of incidence, measuring SP and average. All values are absolute. Unique feature is that we are able to measure really small samples, like 4 nanometers as standard. But this year we were able to measure the sample with just 700 microns physical dimension. And on the right hand, you see the system which was introduced this year in Munich, designed specifically for long wave infrared measurements. And this is not FTIR based technology. This is a truly dispersive type system with gratings and polarizers inside. Same case, fully automatic, capable to measure from 0 to 60 degrees angle of incidence, also SP and average polarization. For this system, the quite unique feature is that we can place here a sample like your palm, that size. All systems have very big advantage of very small beam divergence, so the beam is really narrow. Fully automatic operation, very high accuracy measurement results are being delivered by these systems. And if Antonio, you can switch over to the next slide. I think that values, they speak more than any words. So these are the 2 examples of real measurements. On the upper part of your slide, you see broadband laser mirror reflection measurement, and the yellow area highlighted is shown on the right hand. You see the scale is just from 95 to 100%, very low noise, very high accurate measurements. No values exceed 100%. And on the bottom part of your slide, you see again laser mirror, but the customer requested to measure transmission. And the challenge was to measure at 42, 44, and 46 degrees angle of incidence, S&P polarization. And you see on the right image, the area is scaled from 0 to just 0.8% transmission. You can see the very good resolution of each spectra and very low noise, which is standard in our system. These are the technologies which we are delivering to our customers worldwide already for 14 years. Thank you very much for the time given to speak a little bit about our company.
Thank you, Taras. And anybody interested, you can reach him here on the chat and also contact us later on, so you can be connected to Taras. And our next sponsor today is Modulite, and I think Tommy is here in the room. So you can present a little bit.
Thank you very much, Antonio. So my name is Tommi Hakulinen. I work as a product manager here at Modulite. So Modulite is a laser manufacturer based in Tampere, Finland, with sales process in the US. The company was founded in year 2000, so we have over 20 years of experience in various laser technologies, such as laser diodes, fiber lasers, DPSS, and VCSELs. In 2021, we did a successful IPO and got listed in Nasdaq First North Helsinki. We are probably best known for our work in life sciences and more specifically in our key strategic areas: oncology, ophthalmology, genetics, and diagnostics. And we are the only vertically integrated medical laser manufacturer in the world, from chip level to system. But how this relates to today's agenda, our product line ML6600 is a flexible subsystem platform with wavelength range spanning from UV to 2 micron, so that enables wide range of applications. In the context of optical metrology, it is used as a light engine, so plug and play laser source integrated with all the necessary electronics and optionally also beam shaping optics. Relevant applications are semiconductor material analysis, thin film metrology, and wafer defect detection, to name a few. A unique differentiator of this product line is cloud connectivity, which enables, for instance, predictive maintenance, but also new business models like pay-per-use. And should you have any questions, I'll share my contact details in the chat so you can reach me afterwards. Thank you very much.
Thank you, Tommy. And our last sponsor today, we have ACM, that they cannot be here due to some schedule conflict, but they asked me to present this slide for them. ACM is the German subsidiary of Actar, and as probably most of you know, Actar is an Israeli company. They specialize in the development and applications of ultra-vac and light absorbing coatings and also coated foils, with three main applications for the products: suppress stray light, absorb laser power, and also create high emissivity surfaces. So if you're interested in this kind of light absorbing and ultra-vac coatings, please let us know to put you in contact with Actar Group and ACM. And let's go with the group of companies that we are present today. As you can see, we have a quite complete supply chain with companies from the different perspectives and point of view from the whole supply chain. And it was quite interesting because I saw at the beginning when preparing this slide that, of course, we have companies present that are metrology manufacturers that are happy to reach end users, also to reach perhaps coating and filters companies, so they can supply the products for the characterization, but also a lot of interaction between them and the optics and micro-optics manufacturers, as they can use the product for the characterization, but also develop optical components for some of them. The same with the R&D groups, because some of R&D groups can be users, but also can be developers of some new technology. So I see a lot of interactions. And of course, with the final equipment, as we have some companies that are working in manufacturing devices for different industry, metrology is also very important for them. So as you see, a lot of synergies today. So I hope the presentations of our speakers are going to be as interesting as I discussed with them. And let's go with the agenda. So we will start with a presentation from Toralf Scharf, MicroOptics. Then we will have Tata Steel, Frenk van der Berg, Imaging Optic, Rafaël Porcar, and the Optics, Kevin Contreras. Then ACE Optics, Andrés Cifuentes, Murat from Optofidelity, and we will close with Optocraft and Christian Brox. So Toralf, I think you can share your screen. You are quite far in Asia, in Hong Kong. So thank you for being here so late for you. I will stop sharing my screen and the floor is yours.
Thank you, Antonio, for this introduction, and welcome everybody. Oops, just 1 second here. So I'm not sure what to see now anymore here. Maybe like this.
No, it's good. Yeah.
Thank you for this introduction. I'm happy that I can present a little bit of insight into the metrology aspects and problems we face when we do micro-optic characterization. I think you know probably already a little bit Swiss MicroOptics as a player in micro-optics fabrication on different markets. So we are producing classical micro-optic components like micro lenses, beam shapers in fused silica in etching technology. We produce also printed optics on glass, polymer on glass technology. We have a portfolio on diffractive optical elements, and we also go a little bit now into 2.5 dimensions with more functionalities, like you see on the left lower corner with prism lenses, as we call it. So this is a mixture of lenses on one side and prisms on the other side to change directions of the different light path. We produce in Switzerland with more than 130 people and in our own fab, and we try to grow as fast as we can to serve the market with different objects. So if we go a little bit more technical, this is what Antonio has asked for. Our main dimensions are shown a little bit on this slide here. We have usually lenses, and we have also sometimes, as you have seen, prisms or steps, which we need to characterize and to measure, where we, of course, want to have very high quality of the measurement in surface roughness measurements and shape irregularities and all these kind of things, where sometimes we break this thing down to optical functions. Sometimes we break it down to surfaces, very often the surfaces which we have to characterize. While you see here the different parameters, usually we don't go larger than 5 millimeter with the lenses. Usually it's 2 millimeter and below. And we start at about 20, and we have height limitations for different technologies, which does not exceed 500 micron. In etching, we usually go not higher than something like 50, 80 micrometer, for instance. We realize spherical, aspherical surfaces as a standard product, and some free form surfaces as a little bit of a special product for our customer, which causes, of course, then trouble in the characterization. You will see this in a second, how this should look like. Don't want to get into, give you a few examples of these structures later, so I don't go over the whole details of this slide here. So when we do a measurement of our surface, usually the client is specifying the surface and not the function, so we need to measure the surface. So we have instruments which can do this, which creates usually a lot of data, because we have on wafer where we work on 200 millimeter fab. You usually have something like 30,000 lenses more, or sometimes less, but this is a rough estimation. And we usually have structures which are getting more and more challenging in slope and lateral resolution. So the small structures, of course, are challenging lateral resolution, the other ones in slope. And because we are doing micro-optics, many of these instruments and of the things we are using go with a magnification in like in the microscope. And so this causes, of course, a lot of trouble. Once you have the measurement of the surface, you still need to have a data preparation. You still need to have a kind of communication channel with your customer, which is usually an ideal surface which he has defined, and then you try to fit this and see the deviations from the surface, which means that you discuss with your customer the surface parameters and irregularities. And this is actually the agreement which you usually have on delivering a good or bad sample. And of course, all this, and this is the most important part, sometimes should be done on a level where we have calibration standards, where we have a well-known standards, even already for the measurement principle itself, because otherwise we cannot certify our measurement technology due to ISO or even ERTF standards, which is necessary in our case because we are ERTF certified. I think this gives you a little bit of outline how this works usually. So if we look what would be the ideal measurement tool of today, because we need to measure surface shapes, it should be a tool which has no contamination risk. So actually best is non-touching system. It should be, of course, fast, because we have many objects to measure, which get more and more challenging because we have increasing numbers of objects. Customer wants to have a design of everything. So something like 1 second per 1 millimeter square field would be kind of an acceptable value. Of course, a large field of view is necessary because the objects get bigger and bigger, and we don't want to stitch actually too much because this is very slow. One very important fact is that we need to tackle more and more high slope angles. So it gets more on 45 degrees, and even bigger slope angles gets a very challenging situation, because with standard microscope observation technique, you will not be able to see this very easily. I give you an example of how this looks like in a second. And a recent development on our side is that we all push now for the 300 millimeter cases. So we want to go on 300 millimeter surface substrates, which means that you also have to have high precision tables to manipulate your object, to move it and to set it precisely. All this at, of course, very, very low noise of the measurement system itself. Because if you want to measure 5 nanometer steps, of course, your noise has to be lower than this. It has to be extremely reproducible. You don't want to have limitations of the surface, means that materials should not play a certain role, which you can imagine is a problem, for instance, for touching instruments, because the tip touches different materials in a different way and can lead to problems. If you have scanning profilometers, for instance. Of course, we want to have a calibration, which is, if we are lucky, automatized. So we press a button, it is self-calibration all over. And what we do today is that we have our own evaluation software, which gives us freedom in operation. But of course, it would be much more convenient to have something which you can just buy and which gives you kind of certified output. Yeah, and of course, everything should be very easy to use because we don't want to think much. If we have to think, then usually we are lost somewhere in translation, how we say it in some of the movies. Today, we use all kinds of technologies which you see here: interferometry, confocal scanning, stylus profilometry, and we have coordinate measurement systems. So this combination with all these, we can survive and can develop a good measurement methodology. Some of these things are very precise. Interferometry usually gets very precise results. We have in confocal scanning, you have a kind of relatively cheap system. It's not as good as it could be probably. For the very high slopes, we go with stylus profilometer, and then for the coordinate measurement system, it's just for positioning. Actually, this is what you usually use. It's a normal microscope imaging system with image processing. I think you are aware of this kind of techniques. I give you two examples of cases where we have tried to compare a little bit the different instruments. You see here the different instruments which we have used for this. And we show an example of a reference sphere. You see here we start on the right side with this graphics. Actually, that's maybe I can even go for this laser pointer here. We start with this graphics here. You see the different fields of measurement which we have here. The dark one is the ellipsometry measurement. Actually, this is a stylus profilometer. Then we have a 20x objective for the confocal scanning, and then we have here something is an interferometer, which is a stitched measurement on a certain field here. And out of this data, you can go back to your original data of the sphere, which is here a sphere with a radius curvature of 1 millimeter, and you see the different quality of the results here. So the next view usually provides very, very good RMS values because it's very well calibrated and maintained. The Scharf has a little bit less good RMS, but it's a very, very slow measurement system. And the confocal scanning provides a very fast system, but it also has a kind of relatively bad measurement quality and is not able to reach the high angles. And you see here also, of course, the best measurement system, which is only measured this square field, misses a lot of information which is hidden here on the left of it. And the other side, you see here a little bit the residuals which we can achieve in a plot. You see here there's for sure some kind of calibration problem in the confocal scanning system. This one less, and here you see this is equality with a very coarse sampling, actually, of course, of the Scharf system. So, of course, the best would be to have a system which can cover everything in a very fast way, but doesn't exist. You see, this is already a kind of problem here. To compare these systems is not actually possible because you don't have the same information available. To give you a second example where we investigated the possibility of measure extreme slope angles. So here we have a system which works in transmission on digital lithography. So you shine light through, you reconstruct the wavefront, and then you can figure out what is going on your sample. This kind of technique is not traceable back easily to conventional standards, and it is very difficult to make a kind of certification for this kind of measurement. Doesn't really exist ISO norms for this kind of thing, at least as far as I know. It is limited to transparent surfaces, and it is a kind of functional test, but not really a surface measurement. So we have used this in a very special setting to realize a measurement which is really can be considered as an extreme measurement. You see here, if you can use these kind of systems in immersion. So you put your sample in an immersion field here, and what happens is that the deviation of the ray is, of course, reduced because of the immersion. If you have an information about the refractive index of your immersion liquid, you can measure now much, much larger angles because of this kind of setting. And you see here a measurement of a structure which we got from our project partner Zumdobel in the Fabulous project, which had a 75 degrees slope angle here, which we could still reach. Yeah? What you have as a disadvantage on this kind of setting is that It's not really possible to calibrate it. It's very difficult to get absolute measurements. You can maybe use it for inspection, but not for measurement. And the measurement noise also is amplified with the measurement. So this is a little bit of a problem, but at least you can see what your surface looks like and can access it. You go a little bit deeper into the freeform optical surfaces. We give you a few arguments, but it will be very difficult to measure freeform optical surfaces on a micro-optical application because very often what we use to describe the surface is a parameterized version of the surface so that we measure 4 parameters and not have the full surface to be characterized. For a spherical surface, for instance, we go for arc and conic and then tilts maybe, but there's a limited set of parameters. If you have a freeform surface, the set of limited parameters gets very big, and you have in numbers, and that's kind of very, very problematic. If densely packaging of freeform, sometimes you don't even find the structure where you want to measure. What it means that you cannot break it down to identical optical units, which you can then compare. So it's a kind of thing which is has a distributed function over a large field, and it's very difficult to measure this, because then it would mean that you have fields of measurement of about 10 millimeters, and you need still the nanometer precision. Slope angles is always a problem, and as I said, the function is distributed over the whole array. And it's very difficult to bring this thing all together to then really say what you measure. This is a very challenging situation. For the moment, I think there's no really perfect solution to it. It's only for very, very flat slope angles you can probably attack it, but then still you are stick with something like a millimeter range of field of view, while the element usually gets bigger and bigger to 10 millimeters. You see an example here of some kind of freeform machined surfaces, which we realized with our partner UPMT in Wieland's in TIC. So to come to the end of this presentation, it's the variety of the different objects makes it very complicated to work with a single instrument for the moment. It doesn't exist. Field of view, slope angle limitations is well known. I don't need to tell you something about this, but we have realized that aberrations of the objective is a really, really challenging problem, especially if you want to go to the best quality ever. So here you need very, very careful calibration and very fair recalibration every time you measure something. In arrays, usually you can measure relatively fast. And repetitive, so that's not really a big problem. But if the array has a distributed function and gets non-homogeneous, then it gets, of course, much more complex. For the moment, there's no tool which can do everything. So we mix the tools and we work on the methodology to have the best outcome. Some of the samples I told you already were realized within Fabulous, actually, and I was just to mention this here. So this is the pilot line for manufacturing of freeform micro-optical structures, which is mainly concentrating on printing and hole-to-hole and hole-to-plate technology, where we are a member and where we used to have a few examples here for me to show you a little bit more fancy things. Thank you, Antonio. Thank you, everybody, for listening. And if you have questions, please don't be shy. Thank you.
Thank you, Toralf. So we have time for questions, and I encourage you to raise your hands so you can make your question directly to Toralf. I can perhaps start with one related to standardization that you mentioned, for example, in the case of the extreme angles that you can perform some measurement, but there is no standardization. How do a company like SUS MicroOptics works in this direction? Do you have contact with committees to go to a standardization of tools, or you are just waiting for news from the industry?
So we are screening regularly the new ISO norms which are coming out. We are part in some of the committees, but it's kind of moving very slowly, and usually it just gets it's not very fruitful discussions. It takes time, and then it's kind of also a little bit closed community sometimes. So we ask our suppliers. So this is actually what we try to do, and push them to go with the bodies to confirm the measurement principle. Yeah.
We also have a question from Rafaël from Imaging Optic.
Yeah, just a question out of curiosity. So thank you, Toralf, for the very kind, very nice presentation. You introduced a clever way to make samples compatible with the dynamic of instruments sometime, which is by immersion and adapting the refractive index. I was wondering, for you as a manufacturer, how is it? Is it an issue then, the cleaning of the optics, and how you deal with all this preparation, and how is this affect, let's say, your routine or whatever?
Yeah, so there in some of the fabrication processes, you even have an immersion situation. You can do it like this. If you stamp, for instance, and replicate, you have immersion situations. Yeah. In other cases, what you usually do is you have a test sample which is thrown away afterwards. Yeah, so it's solved in a kind of good way, and you have losses. Yeah,
Understood. Thank you.
We have another question from Kerdri, from Jorge.
Hello, Jorge Sanchez from ATF Kerdri. Very nice presentation. Hello. Really appreciate it. Just a question concerning continuing with this last question. Is you have referred about calibration. How do you proceed? In other words, especially for dynamic situation, do you have a really need as a complementary stage perhaps for your customers concerning mirrors, optical mirrors for calibrations?
So what we usually do is we have developed a kind of set of calibration measurements which we do. The instruments which is linked to step height, flatness, radius of curvature, and some other maybe objects which we have as calibration objects. And of course we need for this calibrated objects which we get from certificated calibrated objects which we get from bodies which we have to buy, and some of them are available, others are not available. Yeah.
Okay, we are specialists, especially in one site inside the ATF group. We are very interested in exploring synergies with you concerning this type of small or adaptive mirrors for your systems. So delighted, if possible, in a later stage after this meeting, to have an informal, at least, talk with you. Thank you very much.
So feel free to contact me. I'm not sure if Antonio, if my contact details are somewhere available.
I can put you in contact with Jorge.
Right.
Good.
Thank you.
Perfect.
Yeah.
Thank you.
Final question from Andrea.
Hello, Toralf. Andrea Lovera from
Hello,
I have a question about the Linsatec machine that you presented. So when you say there is no standard, it means that you get measurement which are, let's say, relative to each other correct, but there might be an offset with respect to reality, or can you elaborate a bit more there?
It's relatively easy. You don't measure the surface shape in this case. You measure the optical function somehow, and you can use it for inspection to compare one and the other. But you cannot easily trace it really back to the surface shape because there is uncertainties on the liquid which you use, which as an immersion liquid. So if there's a small error there, then you have a problem. Yeah. You also need to know somehow the refractive index of your base material, which sometimes is very challenging to get in a very, very high precision. So, and this means that you have a good inspection tool, but you will not have a surface measurement tool.
Okay, that's clear. Thank you.
Thank you, Andrea. And thank you again, Toralf, for your nice presentation and also for showing all the challenges you find in your industry regarding measurement and characterization. It was really, really nice presentation.
Thank you.
And let's go with our next speaker. So we are moving to a different industry, and we have Frenk van der Berg. It's R&D at Tata Steel, and we are going to learn about the optical measurements also in his company. So Frenk, the floor is yours.
Yeah, thank you very much. Can you see already my screen?
Everything good. Everything good.
Yeah, Okay, very good. Okay, so indeed, my name is Frenk van der Berg, working as a scientist at research and development at Tata Steel in IJmuiden in the Netherlands. And yeah, in my presentation, I will first introduce you a little bit to the world of steel, and just a few minutes, and then we'll focus on the optical measurement technologies, especially focused to, well, a bit in the line with the previous speaker, to the surface topology. So first, when we look at our sites, yeah, we have really an integrated steel production. So it's from steel making, an iron making and steel making up to steel coils, as you see on the right, which are then shipped to our customers, typically in automotive and in packaging, but also for the construction markets. And to go from really these primary products, so the iron ore, and also the coal, well, we have a quite, say, complex route with many factories, as you can see here, to really produce these coils. And in this route, also the semi-finished products. These are also often or sometimes shipped to customers, and also these need, of course, to be inspected, either visually, typically with cameras as well, of course, inspected on the geometry aspects, etc. Also surface defects, this is all automatically done. And the material which is shipped, yeah, that is typically galvanized product, so coated with zinc or tin coated products, and sometimes it's also painted, especially for the construction markets. And we do this on this big industrial site. It's one of the biggest industrial sites in the Netherlands, measuring 3 by 5 kilometers. You see we have an open harbor connection to the sea, where the iron ore and also the coal are transported to and then produced further to these steel coils. And of course, from these products, yeah, many different products are made, whether these are windmills, the cars, the rails, buildings, shipbuilding, packaging materials, furniture, etc., etc. Okay, now I will focus a bit more on the topic of today, the surface topology. Yeah, and already, of course, in this picture, you see quite well how important this is. Typically, when we have cars made of steel, these car surfaces are inspected in these kind of streets where you have this lighting, and you see immediately all kind of defects. And so the surface topology is really important for the product appearance, the look and the feel. But also for the sealability of especially packaging materials, and also the process steps which are done at the customer, typically in pressing, forming, painting, etc. For the manufacturing process itself, of course, surface topology is also very important because it has an impact on the process control and product quality, and also the surface finish. It really is highly dependent on our processing over the entire route. Well, if we look then how this surface texture is formed, well, it's typically in cold rolling operations. So we have the work roll, and these work rolls, these in cold rolling had the fresh strip enters, and then due to the roughness transfer, we get a strip with a certain finish coming out. And here you see some example of topology in and topology out. And indeed, as I said, the process itself has a quite large impact on this texture of the strip. And here you see an example of the effect of wear of the work roll. And so this texture, it evolves, and the roll surface topography on the left, you see an image how it looks for a fresh textured work roll, and on the right for a worn work roll after about 4 kilometers of cold rolling. And you see quite well that, especially in this optical reproduction, that the mountains of the surface topology are chipped off after rolling. So that's the sort of aging that you see. Another aspect which is important is the work roll force. So if you have a very light work roll force, then, well, you see hardly any imprints on the material. With a normal work roll force, then you see directly a different surface topology with a higher roughness in this case. So to show what is our ambition, what do we ideally want, is to inspect the surface topology before and after the rolling process. And so this we would like to do inline and real time and use this data as input to a control loop. But yeah, the challenges are quite important that we have. We have to measure on moving product. So line speed is about 3 to 7 meters per second. And so normally you would have motion blur for a 1 micron lateral resolution. You need to have a sort of snapshot techniques that really acquires all your data in just 200 nanoseconds. That's not all. Also, there are quite some vibrations in the production line. So it's the object itself, the steel strip, as we call it, it vibrates. And also the entire installation basically vibrates. So this is making our life difficult. But, well, this could be your challenge, as we say. And then if we can do this, then if we can measure the surface topology in line, then we can also measure the topology of strip in and strip out, and then do the roughness transfer analysis in real time. If we compare how it's currently done, and especially what's the standard reference for the measurement, so what is used for product release, that is still very conventional, old-fashioned, you can say, the mechanical stylus. That is simply the norm, and of course, we are trying to push also the norms, but as already was discussed in the previous discussion, these discussions go very slowly. So in the optical stylus, well, you will know there's a contacting needle with a very sharp tip of a radius about 2 micron, and we record the displacement of the needle. But also there you can have, of course, issues in this standard. There can be wear of the radius, wear of the tip. There can be also, the contact force can have an influence, the speed at which you measure it has an influence. And you need also to measure multiple tracks to have a good statistical averaging of these profiles. But okay, typically for steel, you would get such a type of cold rolling profile in order with a height difference in the order of 1 micron. If we look then typically at what are the quantities or parameters which are associated to such a measurement, is the height resolutions should typically be less than 0.1 micron, typically 50 nanometers. Lateral resolution in the order of 1 micron. And from these profiles, height profiles, we deduce the roughness values, typically RA, and also waviness parameters, which are a bit the more longer type of shape variations or topology variations. And the stylus speed is in the order of the 1 millimeter per second. But okay, we are also, of course, looking at other techniques, especially in the lab. So what we have or have tested in laboratory to measure surface topology, this either optical stylus, where you do a scan, of course, of such a point measurement, either working on based on laser triangulation or laser confocal or chromatic confocal techniques, or preferred, you can say, optical imaging technology like confocal imaging. And on the right, you see an example of where an imager, confocal imager, is used on a work roll. So you see here such a roll to measure the topology of the roll itself. And some other techniques have been measured before. Well, even holography, also mentioned already by the previous speaker. But okay, these are lab techniques, and we would like to measure really inline. So also here for inline measurements, different techniques have been investigated and also trialed. One of them is angular resolved scattering, where we project a laser beam, very fine beam, onto the surface, and we look at the angular resolved reflection, which tells us something about the distribution of the slopes, you can say. And this is tested. Well, here you see an example installed in line at a distance of about 10 centimeters from the strip and taking a measurement every 250 nanoseconds. A second type of technique is to use laser triangulation, but really with a nanosecond pulse laser, because of course you have to freeze the motion of the strip. And with such a device, indeed, you measure tracks, and you can of course only record when in focus, and you can deduce roughness and waviness parameters. And these techniques, have been evaluated in the manufacturing conditions. And what we have observed is that, okay, they are useful to indeed obtain trends in the roughness during production. However, for product release, these are not reliable enough, unfortunately. Well, also more techniques have been evaluated in the lab, like speckle imaging, like white light interferometry, like wavefront sensing. But yeah, the general difficulty that we always have, if you also look from it from an when you model the interaction with light with the surfaces, is really that the roughness on one hand and the optical wavelength that we are using, they are of the same order of magnitude. So there is a mix of diffuse, of specular, and of multiple scattering. And this is really what, troubles our situation, and to come up with a solution that works. So finally, I can end with this slide. Well, could this be your challenge to inspect in real time the surface topology with some kind of snapshot technology? And with that, I would like to finish this presentation. Thank you.
Thank you very much, Frenk, for showing us all your attempts to bring the optical measurements to your industry, and also your challenge for the attendees today. Any questions for Frenk? I would perhaps start asking about how clean is the surface of the metal? Can it be an issue when measuring with the...
Yeah, it can absolutely be an issue. Of course, there can be dust on the surface. There can also be sometimes, or there will always be some little layers of oxides as well on the surface. And also these oxides, they have of course also interaction, as well as there are often also oil film layers. Because that's part of during this rolling process, emulsions are used, and these emulsions, of course, in situations where they are still on the material, they hamper also your measurement, and therefore I only mentioned these two aspects of, well, first of all, vibrations, and secondly of the dynamics of the whole situation. But there's also the entire industrial situation where it has to work with dust, with even indeed these kind of emulsions or splashes of water, if you like. So you have to condition your measurement very well.
Good. We have time for another question for Frenk. Well, if we don't have any, I hope that you will perhaps find in the next speaker's presentation another tool that perhaps you want to discuss with them more in detail about the technology, and perhaps it makes sense to apply in your industry as well. So thank you very much, Frenk. It was really interesting.
Okay, thank you very much. Bye-bye.
And let's go with our next speaker. We have Rafaël Porcar, he's scientific coordinator at Imaging Optic, and he's going to show us the industry optical testing boosted by lift wavefront sensing. So, Rafael, the floor is yours. You can share your screen.
Can you see my screen?
Yeah, good. Everything good.
Okay. Thank you, Antonio, for the introduction and the added pressure. No worries. So, my name is Rafaël Porcar, and today I'm going to discuss an innovation we brought to the market. We call lift wavefront sensing, and that bring ultra high resolution in wavefront sensing. And I will also review a few use cases we had with customer in industry. Okay. So. So Imagine Optic is a metrology company. We are developing wavefront sensors and optical metrology instrument. So this is non-contact quality testing and optical quality in transmission, or surface shape when we measure in reflection. So we can say we have proudly deployed more than 2,000 sensors all over the world, both in industry and academia, both in R&D and manufacturing. So one core value of Imagine Optic is constant innovation, and this is what I came today to present. And I'm going to start with a kind reminder of what is a Schack-Hartmann wavefront sensor. So it consists basically in an array of micro lenses you put in front of a sensor. Each of these micro lenses focuses a centroid on top of the camera, and what we do is we analyze the lateral displacement of those centroids in order to reconstruct what are the slopes of the phase, and which are the angle of propagation of rays, and from that we integrate, reconstruct surfaces and wavefront. What's important here is that basically Schack-Hartmann wavefront sensor reconstruct two information per sampling points per micro lens, which is the slope in X and the slope in Y. And from that, what you can reconstruct is kind of averaged bit of surface, which are plane surfaces. Question is, from the raw signal we get from this kind of sensors, is there something more that we can do? No, more than just the analysis of the lateral position of those centroids. And if you have a look here to this signal, I'm sharing with you, it seems that it is the case. No, it seems that all the centroids focused by the microlenses are not exactly the same. This one is more round, this one, for example, this seems to be more elongated. So is there something more that we can do? And that's exactly the approach of the lift innovation that has been initially proposed by our colleague at Onera Research Center. And it consists in, on top of analyzing the position of the centroid, in analyzing the intensity distribution within the focal spot. And because we know that somehow when you have aberration, an optical aberration, they have an impact on how your light is focusing. So it's really exploiting this specificity, and it allows us to reconstruct per micro lens a combination of up to 9 different type of aberration. So it allows us that you have to compare that with the previous technique, Schack-Hartmann technique, where you only get 2 modes per micro lenses. Now we have 9 modes per micro lenses, and this is added detail at the scale of the micro lenses, and this translates to increased resolution in the measurement. So now the wavefront sensors, on top of being versatile, easy and robust to implement, they can reach a new level of resolution that we have been analyzing in order to check the performance of the technology. So we sent several complex pattern of phase and increasing resolution on our sensors in order to see what is the improvement in the transfer function of the instrument. And if we summarize, what we can see is an increase in the lateral resolution of the reference sensor by a factor of 4 times in one axis, 4 times in the other one. So overall, it's a 16-time improvement. If you check this visually, that's an example. On the left, you have a map of a wavefront corresponding in this case to a SWIR measurement. So we are at 1.5 micron wavelengths. And at that wavelength, sensors usually has less pixels, and then the sensors also have less microlenses. So here you have a measurement of 28 by 28 sampling points. And when you apply the new lift reconstruction, you can see how big the improvement is. By simply comparing visually the finesse in the map. So that said, we have implemented this technology in all our lineup, from our wavefront sensors up to our instruments. So we have different families of instruments, versatile one where you can combine different modules in order to do your metrology very in a versatile way in the lab. We also have a robust automated instrument, more sought for manufacturing. And what I want to show you is different examples of this ultra high resolution. The first one is in the field of MicroOptics production. So here, this is quality testing of produced microlenses that we do at multiple wavelengths. So here you have two pictures of the test bench testing at in the red and in the green wavelengths. And this is the kind of wavefront we measure in transmission. So these are microlenses. The pitch of them is tenths of micron. So you have to see that here we have more or less 700 by 500 points, which means that here we still have, at the scale of the microstructures, more than one sampling point by micron. We can also isolate one microlens and check for its parameters. Okay. Another example, still in the MicroOptics production, but now produced by injection molding. So what we do with our customer is testing the quality of the mold. We are not testing the optics directly, but now we are testing the mold that is going to be used in order to produce these optics with microstructures. And this is a very complex mold. In one part of the mold, you can see it here on the top map, wavefront map. We are testing in reflection the polishing quality, and you can see here those circles that are made by the polishing tool, and we do iteration, and we help our customer to determine when he can stop the polishing of his mold. And at the same time, in another part of the mold, we are also testing different microstructures. So here we are at the sub-millimeter size, more or less. Okay. We have also implemented the lift wavefront sensing in automotive in order to test protective windows you have in front of different sensors in automotive, like cameras and radars. So in this first case, we are testing the same part both in reflection and in transmission. In reflection, we use it in order to again assess the quality of the mold and to relate the quality of the mold and the shape of the mold to the actual shape of the part that has been injected, because sometimes you have some variation. We're also measuring in transmission. So in this case, with MTF measurement, telling us a little bit what is the optical quality in transmission of the protective window. Here another one, still in the automotive. Here our customers has a very complex optical part, combining plastic together with metal and electrodes. Those electrodes are kind of introducing some deformation in the plastic part. So we are assessing what is the impact of those electrodes on the optical quality by measuring the transmitted wavefront. So again, we can make some profiles or reconstruct in 3D the shape of the part. And last example in industry, so this is glass manufacturing. We are helping our customer to test large parts large for us, meaning 6 inches. They are very thin, plane parallel substrates. So we are measuring them in transmission. And again, when we filter all the low spatial orders, we can see appearing what are the details of the polishing tool on the optical quality. Okay, as a bonus, here I can say that, and that's something we share, all the technologies from wavefront sensing. We can work at almost any wavelength. So in this case, this is an alternative to interferometry, like piezointerferometry, because this part has to be measured at 800 nanometers for its spectral coating, and could not be done with an interferometer. Okay. So as a conclusion, we helped develop and commercialize this new innovation we called LIFT, that brings now wavefront sensors with up to 700 by 500 phase points per pupil, whatever the pupil is. So you can really have great resolution. Tech is achromatic, so it works on the whole visible range, but it also works on the sphere. And we can measure from optics from tens of microns up to 6 inches, both in transmission and in reflection. So that's all for me. I thank you for your attention, and I'm up for any question, I hope.
Thank you, Rafael. So we have one already from Jorge from Kerry. Jorge.
Okay.
You are muted right now.
Thank you, Rafael, for the interesting presentation. Just a question concerning microlenses. Which is the influence up to now with your technology, obviously? Which is the influence of any crosstalk or parasite reflections on your microsystem of lenses? Is it a very relevant effect you should optimize, perhaps?
Well, you are talking about the crosstalk between centroids?
Yeah.
No,
one lens is performing or making some rays out of the geometric approximation, the parasial one out of to the other channel, we could say like this.
Yeah. So honestly, there's no crosstalk affecting the reconstruction when you reach this point where you might have a crosstalk in between the centroid produced by microlenses. You already reach the dynamic of the sensor. That's a limit of the measurement, but you have to be in very extreme conditions, because without this we can still measure dynamics of more than 1 micron in tilt and 500 nanometers in sphere. So it's not something happening that fast. It seems that they can merge very quickly, but if you do the math, it's not that's real.
Okay, thank you.
Thank you very much.
We have another question from Ian Warhead, Lean Development.
Mm-hmm.
Hi, thanks for the presentation. A quick question on Shack Harmons that you're offering. Can they work down to ultraviolet wavelengths, 355, 266, 248?
Yeah, so the limit is the sensor we usually use CMOS sensors, so they are sensitive down to 400 nanometers. In reality, a little bit less than that, but more or less this is the limit for the visible range, and then we have to jump. We have other sensors that are specifically designed for the UV.
Okay, very good. Thanks.
Yeah.
Thank you, Ian. And I don't see any other questions. So thank you very much, Rafaël, for your nice presentation and for showing us some examples also for different industry that you are covering nowadays.
Thank you very much.
And we can go with our next speaker. Is Kevin Contreras. He's R&D manager at Optics. So Kevin, you can share your screen.
Yeah. Okay. Hello, everyone. My name is Kevin Contreras. I am R&D manager at the Optics. So thank you very much for your invitation to speak today. So first, a little introduction about us. So the Optics founded in 2018 with the heritage of the activities R&D on the French lab. So we have actually 7 patents, 3 news in progress. So we are a small company with 14 people, 5 members in the R&D team. So with a strong competence on optics and imaging processing. So we are based in Ilkirch-Grafenstaden, near to the Strasbourg in France. So we have a strong expertise on phase shifting reflectrometry. Our ambition is to be your partner zero defect in your control process. So a little introduction about the phase shifting reflectrometry. It's not the idea is to present you a basic. Sorry.
Sorry, there is some background noise. I don't know.
Oh, okay. It's not me. So
no,
okay.
Sorry, Kevin.
Okay. So I continue. So the reflectometry measurement methods use the law of the refraction, and the knowledge of the arrangement between the camera and the operator. So a liquid crystal display monitor to draw conclusions about the state of the surface by means of observing the deformation of the mirrors image. For automatic visual inspection, it's necessary to know all system parameters, for example, the size and the position of the LCD monitor relative to the camera sensor, and obviously the intrinsic camera parameters. So our devices are based on different configuration and transmission and reflection. You can see in this slide, for example, some pictures about the distortion of the deviation of the light rays when it's transmission and reflection. So with this optical technique, is possible to extract the amplitude and deformation maps to obtain gradients X and gradient in the direction to evaluate the slope, altitude. We have a robust algorithm for the phase reconstruction. So the basic of this our device is based on this technique. So for example, some industrial application, for example, for the detection of these defects or difference origin of during the manufacturing process. For example, scratch, leaks, inclusion, bubbles, the defects originated by diamond turning, for example. So it's possible with the reflectometry to evaluate it and to detect it, this effect. So it's possible also to evaluate it or to measure the flatness. Obviously, the accuracy depends on the field of view. So the reflectometry is very well adapted to the industrial applications. The main advantage is to have a large field of view, but your price to pay is to obtain it at dependent accuracy. So, for example, in this slide, I show you the detection of the scratch on a wafer. The size is around some microns in a large field of view. To right, you can see the difference measurement about the flatness for both sides of the transparent piece. So in reflection, we have two instruments, two devices, quality sensor 100 and quality sensor 200. So with different field of view, it's possible to control a specular surface, painting, texture, and surface properties, plastic and composite materials, injection molds also, paper, carton, mirror, glasses, metals, and ceramics. So we can detect it orange peel, for example, or the defects in the painting. So we have other versions about this configuration. We have the quality sense 400. So for the inspection of the effects of the windshield, and quali lens 200 for the watch glasses, for example, and optical lenses, filters. For example, in the picture, you want to see the watch glasses is very critical in the industry because it's very important for the luxury industry. With this device, so based on the reflectrometry, it's possible to inspect all thickness of the material, not just in the surface, really in the defects in the material. So for the ophthalmic, we have a quality lens 100. It's very it's a system adapted for the ophthalmic industry. So some properties we can very excellent repeatability and reportability. We have not alignment of the lenses. It's a fast measurement, user-friendly interface about this software. And we have the flexibility for developing new functionalities. We can customize it, develop. So finally, for the application in the industry, we have other device on the quality lens 150 for the inspection, for the automatic optical inspection, for the intraocular lenses. In this case, it's possible to put different large number of the device or these small lenses. It's possible to detect the defects localized and detection of the different defects. So we have also quality lens 100 for the contact lenses and IOL. So finally, we have the quality lens 300 for the optical inspection of the e-glasses, where you can put between the LCD monitor and the camera. So finally, we present the optics as expert for the defect detection in transparent and reflective materials. So we are very optimistic about the future of the optical reflectometry for freeform and microoptics. So thank you for your attention.
Thank you, Kevin. Thank you very much for your presentation. And we have time for questions for Kevin. I have one regarding the famous epic question, because I saw what's the Optics offering regarding the development of your products. Do you have any need or any challenge for the audience regarding one of the components you can use? Can be illumination, can be optical component that you use. Do you have any need or challenge for the audience?
Yes, exactly. So we are open to work in partnership, for example, for the different manufacturing in optics. So, but nowadays is our business process to very oriented to the ophthalmic industry. So, so we are open to discuss.
Good. I don't see any other question in the audience. So Kevin, thank you very much for presenting your technology and your device. And we can move to our next speaker. It's a pleasure to introduce Andrés Cifuentes. I know him for a few years already, CEO at ASC Optics, and he's going to present his high precision dimensional inspection for industry. So Andrés, the floor is yours.
Thank you, Antonio. It's a pleasure to talk to you again, as always, and to be here at an EPIC meeting. I appreciate the invitation and being able to share some results from R&D activity that we carry out at ASC Optics related to metrology that could have applications in industry. Okay. So I kind of focus on two areas that I want to discuss that are here on the left, which is something that we've been calling high precision large area metrology. And then a second area that also came out from our R&D projects at ASC is inline micro inspection. So I spelled that wrong. Sorry about that. And then just a very quick review of ASC Optics. We're an optical design and assembly and integration company of optical systems. We're a small but a quite innovative team in the field of optics and photonics, working in different fields. One of them being some applications in metrology, as you'll see here. We don't, kind of a difference from some of the other great speakers that have been before me is we don't have a off-the-shelf or an instrument per se, but rather some technologies and experience that have applications that we can further develop or customize for our potential customers or partners. Okay, so I'll jump right into it. So where does this high precision large area metrology comes from? So at ASC, we worked for a long time, for several years, in developing and testing basically what could be considered a LiDAR system for the inspection inside what's called the tokamak, the chamber inside of a fusion reactor that's being built at what the experiment is called ITER in the south of France. So it requires an optical inspection to help determine the erosion that is due to operating the very high temperatures, plasma and the very high magnetic fields inside of this chamber. So to do that inspection, one technique that came up, and that's what we explored, was based on optical metrology. So we used the scanning system to look through to scan areas within a chamber, to be able to make a reference model of the 3D reference model of the inside of the chamber. Difference from what you can consider, let's say, a typical LiDAR for other types of application. That's why this is definitely more industrial in the use case, is that it has micron level precision at about 10 meters or less, which is definitely not typical for a LiDAR system. And we did have to make it compatible with harsh environments, which maybe in all industries not required, but it does give us, let's say, a unique experience in working in very harsh environments inside of the ITER tokamak, which is high vacuum, high radiation, high magnetic fields. These kind of things that complicate a lot in the measurements. We did a lot of work in this area, but I kind of focus it here on just kind of the results of the metrology itself. So we ended up being able to make a 3D mapping of the elements inside the ITER tokamak. We could detect any damage or erosion of the components or the tiles that the chamber uses. We did a complete optical system design and integration and the whole test campaign to validate and also find the limits of the resulting technology. And we finally were able to package it into something that could be put into the ITER cartridges, what they call their cartridges. And we did, as I mentioned before, the implementation and testing. So, yeah, you can see my screen. So basically, we ended up finding a combined solution that solves both the metrology, what we called the metrology and the viewing channel. So we have a metrology, so a measurement, but we also have a view, so a 3D reconstruction. And that's what I'm showing here is a 3D reconstructions, which are a lot more fun to see, but behind this, there's a system of measurements. So the metrology channel was based on a frequency modulated LiDAR, and this gave us the absolute distance measurements. And then this was combined with an amplitude modulated LiDAR, which gave us the surface viewing. So not each of these techniques by themselves wasn't enough, but we devised ways to combine them to give the functionality that in the end was required for the final application. So here's just some views of the raster scans for the 3D reconstructions. We can measure at 10 meters. You can see here the top image is tiles. This image is just a big stool, but we wanted to show that you could, at 10 meters, you could actually capture this with precision, a larger area, but also a smaller area. And that's why we scanned this coin here at this euro coin also at 10 meters. This particular solution was very slow, but that was just due to the availability of products or components that were compatible with that particular harsh environment. So that's not a particular limitation of the system itself. And then all of this that you can see here was captured and processed and displayed by our own custom software development team. And then the fun part is that we find that this could have applications in industry, and that's why we're here today. And I thought this was an excellent meeting to participate in. Where have we found some interest, though we've not deployed this product, like I mentioned, in anything yet, but we did find interest in, say, where high precision is required in large areas, like, for example, in construction of aircraft, or maybe high-end automobiles, but particularly aircraft, where, as you can see here, maybe rivet inspection is an important key area for the aerodynamics of the final assembly of the system. Maybe some of the high precision parts involved in making some of the turbines in aerospace. The previous speaker, Frenk, also mentioned some areas where I will talk about inline inspection, but where also large area and high precision were required, which we hadn't even noticed. So I'm already glad I came to this meeting. And finally, just in general, like finished product quality inspections when things are pretty big. So in that sense, to Epic's question, what do we need, like a general need? I'll have a slide for that more specific later, but a general need is if there's ideas or end users where they might find this interesting, we'd be happy to discuss. So that's kind of a wrap up of what we did for the, let's say, large area, the LiDAR inspection with high precision that's coming out of the work we've done for ITER, and that we can apply, luckily, to industrial solutions if needed. And now we can jump to kind of another area of development that we took on some years ago, based on or coming out of a European funded project. It was actually, I think it was the last of the FP7s at the time. And this is basically what we tackled was the initial idea was making micro devices for use in medical applications. And one of the devices was microfluidic chips. Our challenge within this project was to be able to inspect those chips compatible with production. So inline inspection of microfluidic chips, both in depth. So because we wanted to be able to quantify the quality of the chambers, of the micro chambers for the fluidics in those microfluidic chips, and then also in area. So we had to be able to measure the details in area. So we ended up combining what we called a 3D high-speed inspection based on optical coherence tomography combined with machine vision. We had a patent behind that as well. So we started developing our own OCT system with a particular solution to make it quite robust and less sensitive to the parameters or the noise or the environment in a production plant. We use the machine vision to guide the laser tool, but also to do lateral inspection, as I'll comment a little bit later. And then we finally made some demonstrations of the system adapted for inline inspection. So what we achieved is depth inspection of microchannels, particularly for fluidic chips, combined it with that lateral 2D inspection as well. So that whole idea is that as the chips were going through a production line, we could scan them. But then we found that this could be adaptable, different tool configurations. We could have multi-layer samples, as it's depending on how we configure the OCT. We could use it to define the thickness of different samples, as long as it was transparent to our wavelength. And in the end, we were able to demonstrate functionality for that project, and then also for some other potential use cases that we pitched in the past as well, which I'll show you a little bit here in the next slide. So just a quick summary of how it how it went into not production, but into something that we could test and demonstrate. So we actually built the system itself. It's an OCT combined with machine vision. We have it has a particular illumination for the machine vision, looking at the sample with a particular field of view that can be adapted depending on the needs, because we control the optics, the needs, resolution. It's a balance, as we'll see. And then it's divided. We could call it into two channels: the OCT channel and the machine vision channel. And then those two are combined, and again, with our software team, we were able to make the system to interpret the results and present it to a user. So in the end, we're able to obtain a depth measurement and lateral depth and measurement and lateral measurement of microfeatures. So here's an example of a microfluidic chip, how we can measure it in lateral, and it's hard to show here, but you can see the scans. And this would be just a depth, let's say a vision of a depth scan that we would see. Actually, usually would never see this per se, but it's information that we get out of the depth scan. So like I said, it's not as exciting as seeing the lateral stuff, the more visual things, but it's that the power of the system is to look through the material and look in depth. Again, it was customized for inline inspection. We also saw that we could adapt the technology to make it handheld for some particular industries that required to do measurements in the field, let's say. And there's other different configurations that we could make for different production lines. We could get depth and lateral accuracies down to 2 microns. And as I mentioned before, we have our software team that was able to optimize and prepare the data acquisition for a good user interface and showing the results. And finally, in terms of, and this is where, again, I think it could be interesting for the audience, is where could we found some applications besides the microfluidic chips itself, inline inspection of microfluidic chips. We were able to demonstrate that we could determine faults in micro welds in this particular space for needles, but in general, any kind of micro welds where they're needed. So it's a type of surface inspection as well. And it just in general, different types of micro features that are required for let's say this could be a needle patch, which is something that we worked on, but in general, different types of micro features that have a certain amount of area that are in line, that can be susceptible to a combination of depth scans through OCT and raster scans with our combined machine vision. And that kind of sums up what I wanted to discuss about our R&D developments in the combination of OCT and machine vision for inline inspection at let's say relatively high speeds. So I think the important thing I want to conclude with both of those lines that I just mentioned is that we have a really in-depth understanding of how these things work because we developed it, and we're quite open to adapting it to particular solutions and working with partners that want to drive this to a certain area of applicabilities. And then I prepared the specific slide for the very famous now epic question, which is what can we do for you? And what can we do for you? I summed it up in 2 areas. It's customized solutions for optical metrology based on what you've seen above. I didn't mention it before, but for other customers, we already make, we've helped develop and make custom solutions, custom instrumentation for them, and we develop them in series production, which is my next point. We don't only stop at the development, we can also help you deliver your products for your customers or for you if you're the customers. But it's also very important in these meetings that there's a lot of things that we still would like to have solved or things that we might need to improve our products or our offerings. So what can you do for us? So some things that came to mind that are key were high sensitivity, fast detectors. That's really key for the types of things we're looking into now. So we're really open to hearing some developments in that area, if anyone has any. Quite open again, also related to metrology solutions, is fast modulation, single mode fiber coupled lasers. That'd be really interesting to hear about developments in that area. And then we're always looking for reliable partners for precision, custom optics, and custom manufacturing of mechanics. So reliable meaning, good quality and good time and lead times as well. That would be very, very interesting for us as well. So with that, I conclude my presentation, and thank you again, Epic, for this invitation.
Thank you very much, Andres. Really interesting, really nice projects. And also thank you for this final slide showing the both sides of the Epic question. And we have already one question from the audience, from Jorge.
Thank you again. Manuel, thanks for your presentation. I have a question for you concerning your optical designs for biochips, microfluidics, as you say. Can you comment anything on your optical experience design, including black coating to enhance sensitivity and contrast?
Sure. So thanks for the question, Jorge. Nice to speak with you again. It's been a while. For this particular applications, the coatings that we used for the optics themselves were let's say optimized coatings for the particular wavelengths that we were working at, which would be near infrared or shortwave infrared, so the telecom wavelengths. And so the coatings are multi-layer dielectric coatings, but I would say they're relatively standard coatings that we would use. Because of the controlled environment and the wavelengths that we're working on, we weren't too worried about stray light from the mechanical components, but I can say that that is something that does worry us in other projects. And definitely coatings is a key thing, both. So like I said, maybe not in this particular application, but in general, to reduce scattering, for sure, there's value in exploring really good coatings for both the optics and the mechanics.
Just to precise, we have a whole industrial challenge for other similar applications concerning microfluidics, biochips assessments, where black coatings is a key factor to be included in optical designs. And it was surprising for me that, you're not surprising that what my question was whether these additional, not traditional, I could say traditional coatings, obviously it's a key factor as well, but black coatings for the background of your experimental optical setup, whether you included it or not, and it's okay. It seems it's a challenging strategy for you. Thank you very much.
Thank you.
I saw that Ralph from MB6 was raising the hand, but I don't know if you still have the question, Ralph. If not, we can move to Andrea from Pentoprint.
Yes, so is the surface quality of the microfluidic chips plays a role in the depth measurement? And do you have any specific aspect ratio that limits the measurement, say size versus depth?
So the depth, so I did quite catch your question about the surface quality. There is, if I think I understood was if the surface quality like roughness affects the measurement.
Yes.
Okay, so it would, because if it produces too much scattering, we would not be able to penetrate. So there is a level of transparency that's required for this particular type of measurement. So because
do you have a number like to?
Not really, but everything we inspected was, we could say, optical quality. So in terms of RMS, is probably down, to pretty good polished levels of optics. If what we're looking is just surface quality, then it's not so important, because since we're looking in depth, then it was important that it be relatively well polished. But the OCT could be applied for surface, and that's okay if it's roughness. But for the microfluidic chips, and to your second question, the depth resolution is limited more by the configuration of our optical, or let's say our OCT setup, which is a balance between the wavelength band and the sensor that we're able to use, how the resolution of the sensor. Those two things give you a combination, and then the area that we're going to scan. So in terms of aspect ratio, we really, I'd say within those limits, yes, if we went like over a millimeter, we probably started not getting the resolution down to the low single digit microns that we would for the inspections that were required. So that could be, I don't know if that answers your question, but that in terms of that's where the limits were a little bit in our experiments.
Yeah. No, that's clear. Thank you.
Perfect.
I have a final question for you, Andres, because you have this experience with these large area measurements, also difficult environments. What do you think about the challenge that Frenk from Tata Steel brought today to the meeting?
Yeah, I took notes. It's very challenging, very challenging, because it's kind of from looking at it, it's like if I could combine the an adapted OCT and a large area scan, then we can probably help Frenk solve that problem. I don't dare say anything, because the resolutions of 0.1 microns were difficult to meet. But if we're at the micron level range, because of our experience with the scanning mechanisms, I think there is a possibility that there is some application there. But again, I didn't want to overstep and say anything before. But yes,
I don't want to compromise. Just your opinion about the challenge.
But yes, I do think that there's some very interesting challenges that Frenk put forth that might be at least tackled in some way with what we're presenting.
Good. So thank you very much, Andres, for your nice presentation and showing us what you do in this field. And again, if you want to reach Andres, please let us know, or feel free to contact him directly for any possibility you have to cover their needs, or any metrology need that you could have in the future. Thank you again, Andres.
Thank you, Antonio.
And we go to our next speaker. Is Murat Deveci. He's the Director and Business Development at Optofidelity. And he's going to present his optical metrology in AR smart glasses. So, Murat.
Can you see the presentation?
You are not in the presentation mode, but we see the screen.
Okay, just a moment, please. What about now?
Again, it's with the slides and the notes.
All right, sorry about that, guys.
Now it's good.
Okay. Okay, so thank you for organizing the event. Once more, an introduction. So my name is Murat Deveci. Today, I will present about how optical metrology is helping us overcome challenges with AR smart glasses, or in general with immersive XR. But let me quickly introduce who is Optofidelity, who we are. So we began in the early 2000s with optical metrology and test automation. Our first VR optical metrology tester was already developed after the introduction of Oculus. And with the debut of HoloLens, we also introduced our first waveguide-based optical AR metrology and testing equipment. Since then, we've delivered hundreds of different optical metrology systems to this particular domain. Although our company based in Finland, we have a very global presence. Our company has production facilities, Europe, USA, and China. We have 2 different offices also in USA, where I'm also sitting, and multiple different locations in the APEC. And we help our customers with their all needed metrology and testing equipments when they are developing and manufacturing the next generation of headsets and smart glasses. So there are 2 main topics in this presentation. One is focused on image quality and the other one is focusing on the latency. But first, let's even start by talking about AR smart glasses. So I just want to say a few words about how they work. There are various designs based on different technologies. As you also heard from different companies, there are already different commercial products. However, to simplify this presentation and use the limited time more efficiently, let me just focus on diffractive waveguide-based optical combiners that may or may not work with various different displays, micro displays and projectors such as LBS, laser beam scanning, ALCOS, or LED-based solutions. So there are 2 main components in its essence: light engine or light display engine, so-called, and a combiner. So the light engine creates the light. If it's a panel-based light engine, such as an ALCOS, for example, or a micro-LED, it would also use some illumination and projection optics to collimate the light and direct it into the combiner. Then what's a combiner? A combiner transmits the real-world images and displays the created images to the viewer's eye, merging them to create an immersive experience. So in an optical combiner, an in-coupling element couples the light into the waveguide at angles above the critical angle. So through this surface relief grating, for example, this is based on TIR, total internal reflection phenomenon. So the light will propagate down to length of the waveguide. Then another element outcouples the light in a region directly in front of the user's eye, here. So these areas are known as input and output gratings, and between them there is the eye pupil expansion area. For example, some of the most commercially sold products are already using this type of combination, so such as LBS plus a diffractive optical element. So now we know how they work, so let's talk about what is expected from them. So the requirements for the consumer level adoption of AR can be simplified into 2 categories as immersion and comfort. This simplification was originally made by Bernard Kress, currently the president of the SPIE. So let's talk about immersion, which is more related to this presentation. Immersion provides the feeling of being part of that simulated world. This can be called also presence. Presence would require different feelings, which our eyes, ears, skin, etc. can stimulate. So there are multisensory ways of activating the presence. Then there is the temporal part of it, which consists of movements, mapping the environment, and orientation. This is usually studied under SLAM, the abbreviation of simultaneous localization and mapping. Another important temporal parameter will be motion to photon latency, which I will specifically talk about that later. Then there is the comfort part of the experience, which is quite subjective, but there needs to be some sort of general agreement on what is comfortable and enjoyable. However, I will not go further on that due to limited time, and it's not really relevant to optical metrology. So how can we fulfill these expectations? Earlier, we said 2 primary components, the combiner and the light engine, make the AR display architecture. So to build such an AR display, we need to select the right combination of these components. We need to select the right combination by making some trade-offs, based on some analysis. For example, it could be a trade-off between the field of view and the angular resolution, or the coupling efficiency of the combiner with the brightness, for example. which is the case with the micro LEDs, for example. Somehow we must evaluate our design, selected components, individual performances, and eventually the fully assembled AR eyewear's performance and functionality. But what do we need to have to perform those assessments? So we need to have some tools that would simulate the human visual system as much as possible, so that meaningful analysis can be made and the results would be satisfactory. Simulating the human visual system will require the performance knowledge of the human eye, such as the FOV, resolution, sharpness, contrast, and more mechanical and statistical data, such as what is the IPD for these age criteria, and for male and females, what is the eye relief in average, what is the eye pupil size for males and females, and what if under different scenarios, such as what is for the teenagers, what is for the elder people. So here the challenge is using this know-how and building such evaluation tools to mimic the human visual system or the human eye in particular. So now let's a little bit talk about the image quality here. So on the right side, you can see that what is projected into an AR waveguide and the resulting virtual image that appears to the user. These are the real images that we capture. And of course, the expectation is the what that we are giving through the input grading or through the displays other ways. And on the left side, you can see what is given again through the input grading and what is taken out from the output grading. So the question comes down to, does this product produce a nice image? If so, how nice it is? And can I turn this into a metric and quantify it? So before designing an optical metrology system for near-to-eye displays or any type of smart glasses and their components, such as the waveguide combiner in this particular case, one needs to study the human eye very well, which our own optical engineering team have been studying it for years, and they have patented several of their findings, and we turned those inventions into our core elements when we are building this optical metrology tool. So some of those core components have become, for example, this human eye mimicking lens, this opto-eye, this I referred to it in the first bullet point. So this is a type of double imaging conoscopic lens that allows eye point alignment and a single shot of over 100 degree FOV. 100 degree of FOV, which is a little bit smaller than what we are usually having as a stereoscopic human visual FOV. But in real life, we have this also selective visual system, so that maybe all the time we are also limiting ourselves to less than 100 degree FOV. So this is good enough to mimic the human eye's radiometric properties so far. And then there is the color. There's the color parameter of this. So there should be some sort of system to mimic the colorimetric properties of the human eye. So we invented a filter wheel colorimeter, and we coupled that with this opto-eye lens. So it's in this picture over here. So that's how we are now simulating the human eye's colorimetric properties. Then there's the projector. So the projector is used to project something through the input grading. If you remember the previous slides, so you have to put something in order to get something out of it. So with this projector, we are putting all these type of different reticles so that we will be able to see different patterns. Those are projected from the input grading, and we are analyzing the results through the output grading. So in its essence, this is type of a powerful and customizable RGB LED light source. So we have this reticle changer. This is motorized, so you can have different patterns. Comes down to the waveguide's input grading, and then it changes it, and then you are seeing it, and then you are going through the different pattern, for example. Then we had to design a highly accurate robotic platform to accommodate these lenses and also different optical metrology tools. So the problems were that you have to have such a tool to compensate a large area of pentascopic tilts and phase wrap angles. So pentascopic tilt is the angle of the angle of the glasses that you put it. It's on this direction, and the face wrap is on this direction, for example. So with this multi-axis, we turn into a station with 16 axes. With this allowed us to perform this type of measurements. So we can accommodate both this type of waveguides, and we can also accommodate fully assembled glasses, for example. So how we have done this, the alignment and also the precise movements were very challenging. So we utilized lots of different autocollimators, and we also included confocal distance sensors. And as you can also see it over here, we also have a highly accurate hexapod over here to take advantage of that highly accurate 6-axis movement. And in addition to that, we also have different type of machine vision system to look at, for example, the fiducials of the waveguides, so that we know where we are actually relatively located from the input grading to the output grading. Once the optical setup and the robotics are integrated, so this sort of unique AR optical metrology system has been born. So with this new system, now we already have AR customers, AR companies, so they're able to measure this type of image quality metrics. So the most common metrics over here are field of view, distortion, and AMTF, and also I will say the contrast, for example. Efficiency can be measured quite easily. So it basically means that what you are giving in terms of, let's say, in terms of light power, and what are you getting out of it from the output grading. Or it could be also see-through efficiency. You can just imagine that you are putting a flashlight through a glass, what you have been putting it here, and what is it that you are getting out of it from the other side. And the ratio would be the efficiency, for example. And here I put a small graphs here to provide you the understanding of what kind of spectral transmitters curves that we are getting. These are pretty close to the ideal tri-stimulus XYZ curves. Then, after measuring this image quality of AR waveguides, we then started to question, is the grading quality high enough to even ensure high image quality? So while searching for this answer, we realized that there is not even an optical metrology tool to measure the gradings with the needed accuracy. There are some traditional tools such as SEMs, but the accuracy and repeatabilities were not good enough to measure this type of AR waveguides. Then we were able to build a lithrodiffractometer to measure grading pitch and orientation. If you're unfamiliar with lithrodiffractometer, a lithrodiffractometer is an optical device that uses a laser beam to illuminate a sample. The grading reflects the diffraction order back to the laser, which is then directed toward a camera via a beam splitter. With direct reflection from the grading, we can calibrate the sample rotation stage to measure diffraction angles accurately. By building this optical metrology tool, we achieved a way to analyze the AR waveguide gradings. On the left side here, the pixels color indicates how much the grading period differs from the nominal period. And it's also even detecting the defects, which has a direct impact on the image quality. So this type of non-uniformities, we have done quick studies. These are directly impacting for example, the color uniformity of the AR waveguides. But the future work will be about linking creating more links between the image quality results and the grading problems, such as those mentioned non-uniformities, and how we can perform these measurements also quicker.
2 minutes, Murat.
Okay, and the last topic is about the latency. So let's now jump into a little bit different stuff. So we said that AR is mostly about immersion and creating a physical presence in a non-physical world. If we want to assess the temporal performance, then we have a couple of challenges. One of them is producing end-to-end, non-intrusive, frame-by-frame analysis of the AR display's performance. Then another one is producing these analyses while moving in at least 3 degrees of freedom, or preferably in 6 degrees of freedom, which we would do it in the real life by wearing those type of headsets. We will be moving around, we will be walking around, so it's actually in 3 degrees of freedom. Then comparing these results of the virtual contents pose to the real world pose. By doing this, we will get the knowledge of motion to photon latency and word tracking performance. So what is motion to photon latency? latency in general is the difference between action and reaction. And in AR, we refer motion to photon latency as the amount of time between the user's head movement, that is the action, and its corresponding display's output reflections, that is the reaction on the display. Users should not experience a delay between the physical movement and the display output to have the best immersion. Otherwise, the sense of physical presence in a virtual world will be lost. And then anyway, any MTP latency of more than 20 milliseconds are introducing the dizziness and the VR motion sickness. A low motion to photon latency will anyway improve the hologram stability, so that a good immersive experience would require a very low motion to photon latency, ideally less than 5 milliseconds. For these reasons, reducing motion to photon latency was critical to provide a good immersive experience to consumer AR users. I also mentioned about work tracking performance. This is mainly referring to find out, for example, what happens when there's user-related changes, such as it starts to move, or what happens the lighting conditions are changing. For example, you are in the room or you are going outside, such bright conditions, it affects the image quality, for example. So we needed to have a tool to figure this out, this challenge. And in that case, these were needed because our customers reported those, and we took this challenge and patented a way of measuring end-to-end latency. So we made a constellation map, which is visible here, that consists of absolute markers with binary codes shown as blobs, these small, tiny blobs. Then we install this to the AR device as an application. These absolute marker patterns move in the virtual world using the AR device's own virtual world engine, such as the OpenXR or Unity or some other stuff. Then we needed to observe and track these blobs. As an observer, we have a smart camera inside the eye slots of a 3D printed head. Just like the human eye would look at the glasses, we simulated that by putting smart cameras into eye slots of a 3D printed head. Then we made this 3D printed head to wear the AR device. Then camera looks at the center of the sphere so that the 3D virtual world orientation is detected when the camera is looking at these blobs in the virtual world. And then we represent the results in different angles, such as in yaw, pitch, and roll. And then we compare the robot's motion, which we take it from the encoders. Then we say that, okay, you are this off in terms of the latency when you are viewing this virtual result. I'm about to finalize it. So very quickly, so AR displays are in constant development mode. We don't know what will be the future. Maybe there will be not a waveguide-based solution in the near future, but we will work on it. We will develop more optical metrology systems, and we are constantly listening our customers and the market, and we are also looking for collaborations. As mentioned, we are only testing here two different components, essentially the light engine and the combiners, but there are hundreds of different components in an AR smart glasses. And if you are in this domain, please come to us and explain us more challenges with the different components. We are ready to take those challenges in and turn those into a solution. And also the mass production phase eventually will come for AR smart glasses. And we are looking for ways to improve our testing times. So if you are an automation company, if you are working on these domains, also you can contact us and we can collaborate on ideas of how to improve the testing times also. So thank you very much for listening. It was, quite fast, but I hope that I covered enough.
Thank you very much, Murat, for this good review about all the capabilities, all the metrology tools you are building, and also the challenges for the future, because as you mentioned, we are starting with this kind of products, and there are some challenges probably undiscovered. We have time for one question or comment regarding potential collaboration with Murat and his team. Well, if not, feel free to contact us back, and we will put you in contact with Murat to discuss more in detail. And let's go with the final speaker for today. I have the pleasure to introduce Christian Brock, sales manager at Autocraft. And we are moving now to the measurement of the optical quality of windows and lenses using the wavefront metrology. So, Christian, the floor is yours.
Yeah, welcome. And I hope you can see my screen now.
Yeah, everything good.
So I'll talk about the measurement of the optical quality of windows and objective lenses using wavefront metrology. Start with a short company overview. So we are building the Scharf wavefront sensors as our core metrology system that our customers use for different applications in R&D and production for integration into their manufacturing lines. Then there are subsystems and modules which will combine the wavefront sensor with a light source and will define a measurement plane. And then we also do the turnkey solutions for dedicated tasks. So we are based in southern Germany, 35 people currently. We are developing the software in-house and doing the mechanical engineering, and we have our team of optical engineers to take care about these applications. And of course, there is the other departments. And since a few years, we are a part of the MicroEpsilon group that I think many of you should know. Now, for the testing of planar windows, the first application I want to talk about, the basic idea is you have here your optical system under test. You have a collimated light source that you shine onto the system, and then you are measuring the transmitted wavefront. And in case the system is just perfect, you will get a wavefront which is flat, which shows no aberrations at all. In case you have an optical system which has some aberrations on one of the surfaces, or maybe also inside in the bulk material, you will get a transmitted wavefront that then carries these aberrations. So in my example here, we would have such a coma-like aberration, like you have a valley here and a peak here, and that will imprint onto the transmitted wavefront. We measure it, and we can directly qualify the aberrations of the sample under test in that way. A real setup would look like this. So you have a light source, maybe a fiber coupled light source with a collimation lens. Could be the illumination unit on one side, and then there comes your sample under test. And then on the other side, you have a detection unit consisting of the Scharf wavefront sensor and a Kepler telescope. In that way, we can also rescale basically the detection area of the wavefront sensor to the needed field of view, to the needed measurement area of the sample. This is a typical single pass setup. And the advantage of this is where we can do very nice referencing. So we can just take a reference measurement of the empty system, and then we insert the sample under test. And then we get only the aberrations of the sample under test because we can subtract the aberrations of the empty system, and in that way we can get accuracies up to 2 nanometers RMS measurement accuracy. So here's an example where we did some lot testing of ND filters, gray filters, and you see here the wavefront RMS of the transmitted wavefront. And yeah, we can clearly identify some of the samples by their increased RMS value, meaning reduced imaging quality. And just I picked a few examples here, or this one on which has a very low RMS value, where you get more or less a flat wavefront, or for example this one here, where we have a strong defocus, or another one where there's more like an astigmatic wavefront. You can see that here on this saddle shape aberration. So on one side, the slide tells you, okay, we can, when we do a lot testing, we can do good or bad identification of good parts, of bad parts. But in addition, what the transmitted wavefront tells you is also the reason. At least gives you clues or hints on the reason for the good or bad quality that you're measuring, right? Like in this case here, seems like a global defocus on the planar window. So it's not really plane, it's like warped and defocus. Or this one here has this saddle shape aberration on it. Okay, so this as a short example of lot testing and yeah, quality testing. Now, For objective lens testing, these are not planar windows. Now we have optics that create an image of focus. We can use this a double pass setup, which is not so different. We have here our illumination unit, again consisting of a fiber coupled light source collimation lens. Now we couple this into the experiment via a beam splitter. And as we go through the sample under test here now, our objective lens that we are testing is creating a focus. And we need to use a reference sphere, which is basically a concave mirror with a very good quality, to reflect back the light that comes from the sample under test. So each ray that is leaving here is reflected back into itself, and then is transmitted through the sample a second time, meaning we are collecting the aberrations of the samples twice. And then we have our detection unit again here, where we have a relay telescope that does sample imaging. Right, so that way we can test, for example, objective lenses used in mobile devices or in microscopy, or also in automotive industry. I have an example here for a microscope objective lens, which was a 40x 40 magnification lens with numerical aperture 0.65. And we measured two lenses with the same design. So both NA 0.5 lenses, and one lens showed this strong aberration here, spherical aberration that you can see, and the other was relatively good quality that we can also see. Here we measure a Strehl ratio of 0.75. Here we have a Strehl ratio of 0.98. And if we look a bit into the Zernike decomposition, we can see that actually the reason for this difference in imaging quality is coma and spherical aberration that we have here for this lens with lower optical quality. We have a coma and a spherical aberration, which are nearly not present in this lens number 2, which has a very good imaging quality. So as was mentioned before, the Jacques-Hartmann wavefront sensor has a strong point also in being able to measure at different wavelengths. And here's an example where we tested such a smartphone lens at 3 wavelengths, at the blue, the green, and the red wavelength range. And as you can see, the transmitted wavefront is different. And actually the best performance of this lens was in the green for 532 nanometers. So it seemed this lens was optimized for the green wavelength range, and in the blue or in the red we get a little bit increased wavefront peak-to-valley value, meaning a little bit decreased optical quality. So in addition, this system would do field testing, off-axis testing, but here I just wanted to show you as an example, the measurement capability for different measurement at different wavelengths, and what the wavefront sensor can do there. So now I'm already at the end of my talk. So what we can do for you, but basically we share our expertise in optics testing and deliver solutions for optics testing, and we are always looking for special optics and special cameras that we use in our systems. Like, for example, special optics would be also off-axis parabolic mirrors with high optical quality, such parts. Current challenges are the measurement of large freeform optics. I think this is not only a challenge that we are facing, that's a topic that is of interest generally. And what we are currently also working on is product modularization, so that we are able to measure our deliver our turnkey solutions in a modular way. So we have the possibility to customize, but off-the-shelf customization. So that's the goal. Okay, so with that, I would like to thank you for your attention. And if you are interested in further information, feel free to contact me. us, and or maybe there's still time for one last question today.
We have time for question for you, Christian, if there is somebody in the audience. I have one, at least, but I will wait if somebody else have a question for you. If not, I would like to ask if you try adaptive optics solutions in your devices, because you're talking about this wavefront sensing, but I don't know if adaptive optics could make difference in some of the measurements.
Now, so Optocraft does not provide adaptive optics directly with a wavefront sensor, but basically the wavefront sensor is set up to work with adaptive optics like deformable mirrors. So there, the software interfaces are there, and so that's an application that we are realizing also with some customers, right?
Good. And we have a question from Dominique.
Hello, everyone. Thank you very much for your time and your presentation. I have a question about meta optics component like lenses and other complex functions. Are you able to discuss with me and my partners about these subjects, how to measure a meta optics components with different optical functions?
Basically, yes. Yeah. So the meta optics, they, in the end, what they do, they also create a wavefront, like which is in the, at least looked from a distance, which is not so different in comparison to a standard optics. So in that way, if we are measuring just the overall quality of a meta lens, that would not be so different. Of course, if you're looking into the surface structure and characterization of that, that would be a different topic, and that for that you would probably not use a Jacques-Hartmann wavefront sensor.
Yes, I'm looking for a simple test, having first results and not high precision of the details of the structure. Okay, may I contact you soon?
Yes, for sure.
Okay. Very good. Thank you very much.
Yeah, thank you.
Very good. And if there is no more questions for Christian, thank you very much for your time and for presenting your solutions. You see now a poll that we will really appreciate if you can answer, so we will improve for our next meetings. And just to finish, because I know that we are over time, just thank you again to our sponsors. So Actar, Advanced Coatings, SN Optics, and Moduli, thank you very much for supporting us in this event. And thank you for all the attendees for being here, all the discussion, all the questions. And very happy also to see some points of collaboration between the attendees. So thank you again, and I hope to see you next time.
Thank you. Bye-bye.
Thank you.
Thank you.
Bye.
Bye.
Thank you. Bye.
Good afternoon, everybody.
Thanks a lot. Goodbye.
Goodbye.
Thank you. Bye-bye.